So today we're going to transition. Now you're still working on your extrasolar or your habitable planet models, and I found out I put a new file on the website because that subscript thing in Mathematica, that's for subscripts. Like if you put a subscript, then it thinks it's an array, right? So you can't just put subscripts for notation. You've got to. They mean something. So I ran into some problems. So I put a new file up there for you to look at. And today what we're going to do is talk about the Earth and Moon as a system, talk about some properties of the Earth, and then we're going to use the Moon as a chronometer for the rest of the solar system. So I have a little activity. You're going to get to count craters, do real astrophysics, planetary astrophysics. But before I go on, though, I would like to just single Nate out because I forced him to come to class today, so I could do it. But seriously, so Ergo just came out. Do you guys know about this magazine? This is the undergraduate research magazine on campus, and it's the undergraduate research journal, Ergo, and it has stuff in it from all across campus. A lot of these are results of research projects people have done or papers they've written with professors or by them. I don't know, you worked with Dan Bedford as a mentor, but was that a paper you wrote for class?
Yes,
or,
that was a final project.
Okay, so Nate has an article in here called How Much Water Does the Great Salt Lake Need? And that was a paper for your final class. And that was, I'm sure Dan probably read it and said, hey, we should publish this in Ergo.
Yes, you went through multiple reviews.
I'm sure he did, yeah.
Like, here's how it's better.
Yep.
Like, yeah, here's
but this is significant because this is a peer-reviewed journal, right? I mean, if there are people who read this and say, no, you've got to go back and correct this. And it's a great place to kind of, you know, if you publish in places like this early on, that looks really good probably for whatever you do. If you're going to graduate school, if you're going into the workplace, you know, being able to synthesize your work and present it to other people is really important. So I imagine there's some amazing stuff that can be done with the planetarium work. People writing up their activities and their shows and what they're doing. So think about that. If you're doing a research project, you didn't do the research project. In fact, you didn't do the project at all until you've written it up and presented it to somebody. And that's true wherever you go. So anyway, I just want Nate, good job. You should be pleased about that because.
How did it finally came out? Because it was accepted well over a year ago.
Yeah. Well, welcome to my world. Seriously. Yeah, I had a paper. Now journals are starting to do better on this, but the hang-up is the peer review, right? That's the peer review is the big hang-up because I send a paper in and it goes to 3 reviewers who all have very busy schedules, and so, you know, 8 months is good, 12 months is normal, 16 months is not unheard of, right? Now the nice thing about a scientific career though is you can present your work at meetings on a much timelier scale. So there's something that's kind of derogatorily called peeing on your turf. I'm not making this up. You'll put a paper out for publication, you know it's going to be 18 months, so you go around to all of the major conferences and present a paper on your paper so that everybody knows you're working on it and back off. I'm not making that up. That's really what happens, and it can get a little competitive sometimes. I don't like that part of it, and because I'm sort of the opinion that if you can come up with one good idea, you can probably come up with 100. So if somebody steals your good idea, then oh well, you didn't get it published yet. So it's like if you try to patent something, and somebody patents it before you. Well, get off your duff and come up with a new cool idea. So anyway, by the way, for those of you who are thinking about going into industry and perhaps instead of a scientific career. Who is thinking about industry instead of a scientific career? Anybody? Both. There is an entrepreneurs club on campus who talks a lot about how you can patent your ideas. And that's an interesting thing. If you've got ideas and you want to patent them, you want to get them out there, it's a process that's very similar to peer review journal writing. So we kind of put these up here. And I can tell you that I got into graduate school based on the weight of publishing in journals like this. Right? So I was published as an undergraduate in the International Amateur Professional Photoelectric and Photometry journal. And you can still find it online. It was about asteroid rotation curves. And I go back and look at that work and cringe because I made some pretty obvious mistakes. But obvious to me now, not so obvious back then. All right, so let's talk about the Earth-Moon system. What I really want to focus though on is not the Earth and Moon as objects in and of themselves, but how they can compare to other objects we might study. So when we look at planets, what we want to ask ourselves is, what are the processes, what are the properties, what are the measurables and observables that we could take from a planet we live on and apply that to planets that we don't know about. Planets, for example, we just found the smallest extrasolar planet, smaller than the moon, and it's orbiting with I can't remember where the planet is, or where the star is. It's one of the Kepler planets.
How did we find there's a sentence? I'm sorry.
So we haven't talked about extrasolar planets yet, have we?
No.
Yeah, so we found them with the transit method, so we'll talk all about it when we get there. Anyway, we found it, that's good enough for now. That's all you need to know for now, that we found it. And but it's exciting because what we learn on this planet we can apply to that. And I was talking to my astronomy students the other day. You know, we study this planet, we study our other planets in our solar system. One of the most common types of planets in the galaxy, as near as we can tell, are these things called super-Earths, which we don't have one in our solar system. It's a planet halfway in mass between Earth and Neptune. And if you look at the new data, about almost half of the new planets that are being discovered are these super-Earths, and we don't have an example of one of those. So how do we apply what we know on this planet to those things is a really good question. Yeah?
It was pretty cool. Though. Somewhere there's an alien astronomer who's looking out the sky and going, no, we just live on this boring old super.
I know. We don't have any examples of regular Earths. Yeah, mini-Earths. They're called mini-Earths. Yeah. No, it's an interesting thing. I'm working with a gentleman in Potsdam, Germany, about the idea of habitable worlds, and it's entirely possible that this world is not the most habitable. And we'll talk about that when we get to later. But first of all, what I want to talk about is the Earth as a source and sink of energy.
I often wonder if there's kids in an astronomy class on another planet that they just discovered our planet. Like, how did you find something so small?
Exactly. Except they said, and they pointed with their tentacles.
Exactly.
Yes. And then they snorted it and then sniffed the response.
That's inappropriate.
No, it isn't. You could communicate through smell. Most animals do that. What? I have goats. They communicate through smell, boy. Whew. You don't know that? Just come visit my goats sometimes. They stink. Okay. So let's talk about this is on tape. Let's talk about the planets. Let's talk about the Earth as a planet. And I want you to, this is so hard to do that not even NASA considers the Earth a planet. Right? NASA only explores planets off the Earth. But we live on a planet, right? We're as close to an extrasolar planet as you can get by being on one. And so I want to study it from that perspective. So first of all, let's talk about what are the energy sources for the Earth. We've talked a little bit about the one energy source, which is the sun. And the other energy source is the radioactive decay of the Earth itself. And one of your homework assignments, and I've got to look into this a little bit better, but one of your homework assignments starts with this measured value that the geothermal flux from the Earth is about 5 times 10 to the minus 2 watts per square meter. Compare that to the flux from the sun. The flux from the sun is about 1,300 watts per square meter at the top of the atmosphere. Now I say that because when we calculated our equilibrium temperature of the Earth, we got a temperature of 255 degrees. And then I said that the 288 degrees was the actual surface temperature, and that difference was due to greenhouse warming. Well, one of your homework assignments is to figure out what the Earth's temperature would be if there was no sun. So you're going to figure that out. And I'll give you the punchline. It turns out to be about 31 degrees. So that's fascinating to me because I think I misspoke. I think that 33 degrees is not just the greenhouse. Part of it is geothermal energy, which means we are on track to double the greenhouse component, which is 2 degrees. We're going to push that to 4 or 6. So anyway, so you'll get to do a homework assignment with that. I don't remember ever hearing about that before, so I'm still looking into whether that's actually true, but I thought it was very fascinating that without the sun, you get about 30-degree temperature. Yeah?
Is the sun...
What's that? Okay, watts per meter squared. So this is the flux coming out of every square meter of the Earth itself. And so you might ask yourself, how long is that going to take for the Earth to cool off? This is just the fact that it has material made out of radioactive atoms. The radioactive atoms decay, they give off heat. And so the question is how long until the radioactive flux of the Earth goes to 0? So the first thing you want to ask is, what is the time rate of change of the total energy inside of the Earth? So how would I get the, if this is already in watts, what would I multiply that by to get the power output of the Earth? So this is watts per meter squared, and what do I need to multiply that by to get the power output? The surface area of the Earth, right? So we go ahead and do that. That's going to be the power, which we call dE dt, right? That's measured in watts. And that power is just going to be the surface area of the Earth squared, or sorry, the surface area of the Earth, times the flux coming out of the Earth, FGO, to be about 0.6 times 10 to the 13 watts. That's the power output coming out of the Earth, just simply from geothermal heating. For comparison, let me go ahead and turn this on here. For comparison, the total global power consumption of the entire human species, right? So the total global power consumption, the TGPC, which I just made up, is equal to 1.4 times 10 to the 13 watts. So if you could find some way to harness all of the geothermal energy coming out of the Earth, we're good, right? And there are places that do this, right? What are some of the places that do this? Iceland. Yeah, Iceland, half of its power comes from geothermal energy. So I think that's pretty interesting, because we don't really exploit geothermal. There's plenty of geothermal to do everything if we could find a way to exploit it. The problem is, where do you produce it? Where do you transport it to? Yeah.
Yeah, I remember reading a couple articles about geothermal energy. Apparently, one of the big problems is that the hot spots, they give off the energy moving around too much.
Yes.
So Iceland can do it because they have huge stationary hot spots.
Yeah.
They are
right. Yeah, but if you're trying to do it like at the hot springs up here, those hot springs aren't going to be there very long, right? Because it's a fault plate that's moving. Now, of course, that's over. They're not moving that fast. I mean, you could put it on wheels and move it. It moves like a centimeter per year. So you could just put it on wheels and march it along like that. All right, so what is it? So if we want to figure out, so that's the rate. This is the rate at which we're losing energy. So if we want to figure out how long it's going to take for us to lose all this energy, we need to know how much energy we have, right? What do we have in the fuel tank? We know what rate we have. What do we have in the fuel tank? So a good way to do this is to just ask yourself, well, what is the total thermal energy of the Earth, right? And the total thermal energy of the Earth is let's see, total thermal energy of the Earth. If you remember back to your 2220 class or 2210 class, the thermal energy for solids is 3 kT. That's per gram or per kilogram, right? So that's per. Well, I'm sorry. No, that's per particle. And then we have to figure out how many particles there are. Well, I can take the total mass of the Earth and divide it by the molecular mass of the objects that make it up. And if you kind of do a reasonably careful analysis, that's about 40 times the mass of a proton. So if I take the mass of the Earth and divide it by the total number of particle on average, I get the total number of particles. Multiply that by the amount of thermal energy per particle for a solid. This is a rough approximation. I get the total thermal energy. An order of magnitude, that's about 10 to the 31. If I just use a temperature of 273 or 288, I guess. We use a mass of 6 times 10 to the 24. The proton mass is 1.67 times 10 to the minus 27. K is the Boltzmann constant. I throw all those numbers in, and I get about 10 to the 31. So if I divide the rate into that, I'm going to get the number of seconds it will take before the Earth completely dissipates all of its energy. Now this is the reason I wanted to do this calculation, is this is handy for determining the lifetime of anything that's producing energy. A star, if you know the energy output, you know how much energy it has. You can figure out how long the star is going to live. So we'll come back to this type of calculation. And it's you do these types of calculations all the time. This is the mass in the fuel tank. This is the rate at which you're burning the mass in the fuel tank. If you want to think about your car, you could do this in terms of energy and energy per unit time. So if I go ahead and do this, I take the thermal energy, I divide it by the rate. That's going to give me the time, and if I calculate that out, that comes out to about 4 times 10 to the 17 seconds, which is about 1.4 times 10 to the 10 years. So we've got 10 billion years of thermal energy on the Earth. That's our planetary cool down time. And I just wanted to throw this out here for kind of a self-serving reason. And that self-serving reason is there's a lot of energy in geothermal, and it's practically infinite as far as we're concerned, right? So if you can, and geothermal doesn't have to be necessarily volcanic hotspots, right? You could just dig a big borehole 6 kilometers down, and it's 110 degrees down there, and it's 10 degrees up here, right? You can generate energy that way. So I think there's some interesting ideas for how to do this. In fact, there's a very simple type of geothermal that's coming to houses. If you live someplace with a relatively high water table, you can dig a trench around your house and lay a pipe, and then use that to exchange heat to either heat or cool your house. And what you're using there is just the geothermal gradient of the Earth. And it is an effectively limitless supply of energy, because it already produces as much as we make or need, and it's going to last for the lifetime of the solar system. Yeah?
So I think I lost something in your explanation. Why do we divide the mass of the Earth by the mass of 40 protons?
Right, because this is, so the total thermal energy, I probably should have written this down. So the total thermal energy is n, number of particles, times 3 kT. This is the thermal energy per particle. This is the number of particles. So if I divide the total mass by the mass per particle, I get the number of particles.
Why did you take 40 protons?
It's the average molecular weight of stuff in the Earth. So if you take in the iron, silicon, nickel, oxygen, all that stuff, it's about, the average molecule is about 40 times the mass of the proton. So where's our, we don't have a periodic table of the elements in here? Well, I guess this will do. Yeah.
I don't want a nuclide chart.
Yeah, table of nuclides. So what's 40? 40 is
Close to iron, isn't it?
zircon. Yeah.
So, just zircon.
Yeah, iron is way up here. Fe, 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 Fe. Where is iron? 58, I thought. No, that's cesium. Don't get this on tape. I'm an astronomer. I'm not supposed to know this. It's, yeah. It's like, well, there's Mercury.
Venus.
Venus, Jupiter. Where the heck is it? Well, anyway, it's about in the middle of the metals. Right? Yeah. Yeah, that's, remember, so the periodic table of the elements, now we know, looks like H1,
26.
2, yeah, so it's right in the middle. There. How about that? Oh, no, 20M, sorry, because it's protons, we're counting protons, so 20M.
20M sub P.
Sub P. Okay, all right. All right. So that is, what did I do with that sheet of paper? I think I put it away. So that's our cool down lifetime. So the Earth has this geothermal energy, and it's going to stick around for a while. Now the origin of this geothermal energy is from the origin of the planet itself, right? Because we collected enough radioactive material in our development of planetesimals that we are producing enough radioactive decay to carry us out for 10 billion years. However, there's more stuff that gets put in besides just the radioactive materials. Not only do you have all of the refractory materials like iron and nickel, but you have all the volatile materials like hydrogen, helium, oxygen. And are you familiar with those two words, refractory and volatile? Okay, so let me write those down. So refractory is stuff that's hard to evaporate, right? So refractory, I think about it like last night I made spaghetti sauce, okay? So I huck in the canned tomatoes, they've got water in there and tomatoes. And then I simmer it for a while, and the sauce gets thicker, right? The stuff that's left behind is refractory. It doesn't evaporate very easily, compared to the water, which is volatile. And often we call these volatiles or refractories. Refractories, these are materials that are either refractory or volatile. And so this is the stuff that is difficult to evaporate. This is the stuff that's easy to evaporate. So things in the solar system that are refractory are things like iron, nickel, silicon, right? Things in the solar system that are volatile are things like hydrogen, helium, water, other noble gases like neon and argon, methane, methane, ammonia, NH4. See, I know some chemistry. I know a few chemistry tricks here. I know I've got a couple more things besides. Got carbon, nitrogen, sulfur. Right, these are things that are refractory. So what we expect to see close to the inner edge of the solar, or the inner part of the solar system, is planets that are made out of refractory materials because it's hot near the sun. And that's why our planet is mostly iron, nickel, and silicon dioxide, really. So that's why we expect to see planets mostly made out of that. But the other feature of our planet is it happens to have a lot of water and other compounds that should not be here, just simply by the nature of just being here when we formed. So something must have happened. There must have been chemical reactions that happened. I should probably put CO2 in here. Chemical reactions that happened to make these things, or they had to be delivered from someplace where they could form in the solar system, where they could condense. Because whether something is refractory or volatile, where they condense depends on temperature. These are high temperature condensates, and these are low temperature condensates. And so if I go someplace where the temperature is low enough, I can condense water, methane, ammonia, CO2. But that's not on the Earth. And in fact, if I were to make a plot of the planets, let's say this is Jupiter, and this is Mars, and this is the Earth, and here's the sun. The place where you get far enough away from the sun where you can start to condense stuff like water into stuff you could deliver and store someplace is between Jupiter and Earth, or Jupiter and Mars. This is called the snow line. It's just like the snow line on mountains, right? When they say the snow line's at 4,800 feet and you see the snow up there, it's too warm down here to condense water, or to freeze water in that case, but it's plenty cold enough up there to freeze water, so we get a snow line. So the materials, these materials, in particular these, condense out here, but yet what is the major hallmark of our planet Earth? Water. So the question is, where did our water come from? And the answer is, we're not quite sure, but we have some ideas. It had to be delivered by comets or meteorites. Yeah?
So isn't that kind of the big problem with trying to make a habitable planet that runs off water? Is if it's far enough away that it can have water, it's going to be frozen. It's
going to be frozen, that's right. Yeah, so what's going on, right? Because we have water-based life, and we suspect water is going to be common in the solar system because the two dominant constituents other than helium are hydrogen and oxygen. So we expect water to be common in the universe. So you got to be habitable, you got to be close, but if you can't get any water there. So what happens is basically what happened last week with the Russian meteorite. Right, that Russian meteorite is an Earth-crossing meteorite, and if you saw I'll draw another picture up here. They published where they think this thing came from, and here's Mars and here's Earth going around the sun, and this meteorite looks something like this. So in other words, it probably formed out in the area where you can have water and things like that, and then it hits the Earth. So over time, we've delivered water to the Earth. That's a lot of water, yeah. But if you think about it, it's not that much. I mean, so by mass, and to do this is kind of the brain dead calculation, but because the rock has water in it too, the mantle has water in it, but the ocean is 3 kilometers thick. The Earth is 6,400. So 3 squared divided by 6,400 squared is how much water you need, because that's surface area. I guess you have to do volume. So let's do 6,400 cubed by, well, it goes like the cube, right? So do the shell over the volume. Anyway, it's not very much water compared to the planet. Which brings me back to my point of maybe we're not the most habitable planet in the solar system. Because if we were a super Earth, we would have collected a heck of a lot more water, because the gravitational influence would have brought in asteroids more commonly.
It's 1 times 10 to the negative 8%.
All right, not very much. Yeah. So we have to keep in mind that when we're forming the Earth that we started with is not the Earth that we have. So if I want to talk about the primordial Earth, what was its atmosphere like? Well, what? Yeah, but I would preface this by saying, how do we know this? Because we don't know. That was the dumbest thing I've ever said in my life. So we don't know for certain, but we can look at the materials. So let's back up a little bit. We can look at materials that formed in near-Earth crossing orbits, like asteroids, right? That aren't from out near Mars. They're things like the big one that just went past. And we look at the composition of those things, and they're pristine. This is what our Earth must have been made out of. And we can get an inventory of materials and then use models to figure out what would happen in volcanic episodes and get some idea of what the outgas material is and then infer what the atmosphere must have been. But we have no measurement, no direct measurement. That's why we're looking for Earth-like planets, because what we'd like to do is find an Earth-like planet that just formed so we could measure its atmospheric constituents. So there's a lot of debate over what I'm about to tell you, but the primeval atmosphere was thought to have primarily hydrogen and helium, because this could be grabbed from the stellar nebula, right? This is stuff that could be around everywhere in the stellar nebula. And then it also had methane, ammonia. And the reason it had methane and ammonia is because there was carbon. I probably should have put carbon in there. Carbon and hydrogen react to each other, so there were chemical reactions happening. So we get methane, which is CH3, and ammonia. There was nitrogen available. I should probably put nitrogen gas available. And we have NH4 is ammonia. These happened, what?
Oh, CH4.
Oh, you're right. Didn't I just write that down before? Yeah, you're right. Because ammonia looks like this. Yeah, you're right. Looks like a pyramid. So, CH4, NH3 happened because of chemical reactions, because there was lots of hydrogen present, and so we think this is what the primordial atmosphere looked like. Now, in addition to that, these guys, though, and you can do this calculation, it's too hot on the Earth to hang on to hydrogen and helium. Right? It's just, it escapes over time. You okay? Oh, okay. All right, good. Just so long as it's not me. Is my fly down? I always get nervous when people are... That's on tape, by the way. All right, so we lose this, right? But before we lose that, well, let's talk about what happens first. We lose this, right? We do have volcanoes happening. We have comets and asteroids delivering water and carbon dioxide and all this sorts of stuff. And we wind up with volcanoes that give you outgassing. And that outgassing, because of the chemical reactions inside the Earth, are giving you things like CO2 and H2O. The CO2 reacts with the rocks because we have a geochemical cycle called the carbon cycle, and we'll talk about that a little bit later. The CO2 gets sucked up by calcium carbonate, which is CaCO3. So this stuff is getting sucked out of the atmosphere. It's outgassing, but we do have water left over. And we get photodissociation of the nitrogen compound. So the ammonia gets photodissociated, and it forms into photodissociated nitrogen, photodissociated N2. And then the primordial atmosphere starts to look like primarily a nitrogen atmosphere because the CO2 is gone. Methane, ammonia, did I get that right? CH3, or CH4, NH3, water, and a little bit of CO2. So this is our primordial atmosphere. And what's crazy about this is pretty much the atmosphere of Titan. Right? So Titan has effectively a primordial atmosphere. But Titan is a moon of Saturn, and it's not anywhere near the habitable zone.
I can't remember, have we landed for one Titan?
Yes, we have. It only lasted for about 7 hours or something like that. So the Earth we started with is not the Earth we have, because the Earth we have now, if I were to put this would be like, let's say this is 98% nitrogen, and then percents of these other things. So I am totally making that up. We have no idea. And in fact, the only reason we know what those are is because people like Jim Casting model the early Earth, and try to put enough greenhouse gases into it to make it warm enough to have liquid water, and then that's how we get the smattering of these other things that are in there. So here we are. This is what the Earth looked like, not the Earth we have today. The Earth we have today has about 75%, let's say this is today, right? The Earth has 75% nitrogen. It has 23% oxygen. These numbers are approximate. There's some argon at the level of about 1.3%. Wait, what did I do? Messed that up. Let's say 1.3% argon, which is a noble gas. CO2, 400 parts per million. Dang it, did it again. 400 parts per million is CO2. And then water, H2O, is about 1%. And then there's some other stuff in there, neon, helium, a little bit of methane, and krypton. Right?
I hate Superman.
I know. Not kryptonite, it's krypton, which is not derived from kryptonite. Nope. Noble gas.
But is the reverse true?
Yes.
Okay.
Yeah.
So I still don't like it.
Right. So what happened? This is not a habitable world as far as you're concerned, but it is a habitable world as far as life on this planet was concerned, because there was life back then. There was microbial life back then. So what happened?
Oh, bacteria.
Yes. A specific type of bacteria called cyanobacteria. And I'm going to write this cyanobacteria because you live near one of the most awesome places in the world for observing cyanobacteria. Great Salt Lake. You just wrote an article about it. In fact, I will quote from this incredibly well done article. Let's see here. Where is it? You had this whole... sorry, I didn't highlight it. Yeah, here it is. Though the entire lake once maintained a mostly uniform salinity, which varied between 15 and 27%, Gunnison Bay has since 1959 maintained an almost constant 28% salinity. Gilbert Bay is on the other side of the causeway, right? So that is the perfect environment for cyanobacteria. They're pink or purple, and you can see them from space. If you look down at the Great Salt Lake, you see the north arm is purple or pink. So back at about 200, or about, yeah, it was about 2 billion years ago, so this event would happen 2 giga years ago, the rise of cyanobacteria occurred, some natural mutation which caused an organism that could produce oxygen. Yeah?
Quick aside related to the lake.
Yeah.
We took a field trip to the lake during the winter.
Yeah.
And it was snowing, so the beach was white because of the snow.
Yeah.
And the lake was blood red.
Yeah.
It was so cool.
And the ice had layers of, like when I saw ice on the shore when I went out in the wintertime, and it had layers of pink stuff where it had, the water had gone up a little bit and then frozen in there with the layers of ice, so there were little...
We didn't see any ice, it was just white and red.
Yeah, it probably wasn't cold enough. You can get some ice near the edge, and it's not ice, it's not sailing ice, like it's not ice from the lake, it's ice from just the river coming in or something, that's from the fresh water coming in. But anyway, cyanobacteria, you can go out and take a look at those things. Those things destroyed the planet, right? Didn't we talk about this before? I think we talked about this before. They started producing tons of oxygen and poisoned practically the entire planet because nothing there was capable. Oxygen is very reactive, so anything that was doing anything suddenly, you know, it's like driving yourself into your garage and shutting the garage door and turning your car on, right? Because CO is really reactive. You're trained for oxygen, you suddenly replace your atmosphere with CO, you die. And that happened with some of these organisms. But it gave this rise of 23% oxygen. And the coolest thing about this is that the surface of the Earth had a lot of iron in it, but there was no oxygen in the atmosphere, so there were no iron oxides until the rise of oxygen. And then suddenly, the Earth was probably the same color as Mars for quite some time. And in fact, you can find rocks where there was, where you had oxygen content in the water changed, and it would make red rock, and then black rock, and then red rock, and then black rock, and you get these banded iron formations. But that if you go look at the rock down in southern Utah that was formed at this time, it's red. The bottom of the Grand Canyon, red. So imagine the Earth looking like Mars. for about, I don't know, 100 million years or something like that. But then once the iron took up all the oxygen, it started to rise in the atmosphere, and this is the atmosphere we have today. So when we talk about the Earth, we have to be very cautious of the fact that the Earth was not always Earth, and therefore we have to be very cautious when we talk about any planet. Was Venus always Venus? We're going to talk about that a little bit later. Was Mars always Mars? That's the subject of next week's topic. Because we have this tendency to look at a planet and say, oh, that's always been that way. But the Earth clearly hasn't been. And this is the one we've studied carefully enough to know that. So you can't tell me that the other planets, the ones we haven't studied very carefully, are any different from the Earth. So keep that in mind as we go on. So questions about this little story I'm telling? No questions? Ooh, I had a... Oh, we'll do that in a second. I do have a question for you, but we're going to do something first. All right. So in addition to there being surface water, liquid water on the Earth has another very special characteristic that is not shared by all Earth-like planets, and that is it has an atmosphere. And that atmosphere is something that we can study in detail as well. So I want to talk a little bit about how we make some basic measurements of the atmosphere, and in particular how we measure the properties of the temperature profile of the atmosphere, because that's going to be critical. And I have a couple slides here to show you very quickly, because on any planet where you have volatile components, the temperature structure of the atmosphere is going to tell you whether or not you have water at the surface, whether or not you have condensable clouds, which changes the albedo, whether or not you have rain or snow, right, which are all processes that occur on planets with life 100% of the time, as we know, because there's one planet with life and it has a cycle with all three phases of water. So this happens all the time on every planet with life that we know of. So this is a graph of the pressure as a function of altitude. And if you can think about this, we're going to do this calculation in just a sec. But what would make this pressure curve change? I'll give you a hint. There's two things that could make this pressure, two properties of the planet I could change to make this pressure curve change. Let me ask you another way. What would happen to this pressure curve if I made the planet more massive but the same size?
It would become steeper.
It would become steeper because we would be holding the atmosphere closer to the Earth. If I were to make the planet hotter, what would happen? It would puff up the atmosphere, so it would make this curve change. So we can calculate the change of this curve, and we know that curve has to depend on those two things. It has to depend on gravity, and it has to depend on thermal pressure. So let's start by writing down the competition of those two forces and look for a property called hydrostatic equilibrium, because since we're not losing our atmosphere to space, our atmosphere is at least approximately in hydrostatic equilibrium. And hydrostatic equilibrium just means that if I take a parcel of atmosphere, and I'll use a little cylinder here, a little parcel of atmosphere, it's not moving up or down. In principle, I mean, clearly we have motion in the atmosphere, but the atmosphere as a whole isn't flying off into space. So the first approximation, we can call this hydrostatic equilibrium. This thing has a force of gravity pulling down on it. Call that Fg. It's a certain area and size. It's a certain depth called delta R. And the pressure on this thing, since it's not moving, there has to be pressure. The pressure acts from all directions, right? We don't have to worry about the directions on the side because we don't care about that. They're going to cancel each other out. But there is a pressure gradient. In other words, the pressure is not the same at the top and the bottom. And that has to be true because if it wasn't true, if the pressure was the same on the top and the bottom, it would fall due to gravity, right? So we're going to write down the pressure on the top as P plus delta P, and the pressure on the bottom, which is pushing up, as P. And we're just doing this way because of our gravity is negative down, and this is negative down, but delta P has to be a negative number, so we're adding it to the top. But it's really a subtraction. But it's just because of the way and you'll see that when we come out with the derivation. We're really just, we're putting it on the top so that we get the sign out that we want. Because the pressure has to decrease with altitude, right? So delta P as you go up is going to be negative. So I can write down the force of pressure is just going to be the vector difference between these two. So that's going to be P, which is up, minus P plus delta P, which is down. And that whole thing, as we remember, force is a pressure times an area. So I multiply that by area. So that gives us the net pressure. And the gravitational force is pointing down, so it's negative, and that's just G times the mass of the Earth, since we're close to the surface of the Earth, divided by the distance squared, times the mass of this whole thing. This whole thing has a little mass. But I can rewrite that mass in terms of density. If I just say the mass is equal to the density times the volume, which is area delta R, right? I can write down my gravitational force as equal to minus G m Earth times rho a delta R over R squared. And I think I got all that in there. So this is my gravitational force, and this is my pressure force. And they both have to be equal, or sorry, they have to sum to 0, which is not quite the same thing as saying they're both equal. They have to sum to 0, and you'll notice they both depend the same on the area. So the area doesn't matter. So I can cancel out the area. And if I do that, that means I just get the, well, I'll put the area in here for a second. Area P minus P plus delta P is equal to, whoops, sorry. We add in the gravity, Gm rho a delta R over R squared. That whole thing has to be equal to 0. And I've added those two together, keeping my minus sign here. Those things have to be equal to 0. This is called the hydrostatic equilibrium condition. We call this HE. It just means that there is no net force. Sum of the forces is equal to ma, and ma is equal to 0. And so I can go ahead and cancel out my a, because it's equal to 0. This p is going to go away, right? Yeah? And I'm going to get a minus delta p. Minus delta p minus this is equal to 0, which means my delta p is equal to minus G m Earth over R squared rho delta R. So that's my change in pressure as we go up in height. So it's the pressure gradient. If you want to write it this way instead, let me just take my delta R and move it over here. So that's the slope of that line. Rho is the density of the atmosphere. Now we're assuming the density of the atmosphere is independent of height, which is not true. Yeah. But we're just doing this to first approximation anyway. And if you'd like to, there's nothing stopping you from relaxing that restriction, because we're going to do an integral, and you know how to do that. So if you don't like the way we're doing it, you can do it a different way. Can I erase this part, though?
Yeah.
Okay. All right. So what we really want to get is pressure as a function of height. And you'll notice these graphs. We'll see these a lot when we talk about atmosphere. We put the independent on the wrong part. And the reason we do that is so we can put Mount Everest on there and hot air balloons, and it makes sense. Or helium balloons.
Are we sure the altitude isn't dependent on pressure?
Maybe it is, yeah. Well, I increase the pressure, oh, I'm flying up. Wait, it kind of is. Because if you decrease your own pressure, you do go up. So maybe, yeah, maybe that is. Oh, no. You okay? I wouldn't. Just for the record, he spilled his coffee, because they don't know. They don't know. All right. So if we make this differential, we do dp dr is equal to minus gm of the Earth over r squared times rho. If you wanted to take into account the density as a function of height, you could do that. We're just doing this to first approximation because it makes the integral easy. Oh, wait. No, I take that back. We're going to do something else. We're going to take into account the density, not as it varies with height, but as it varies with temperature. And since the temperature varies with height, that will be put in there explicitly. So how are we going to do that? How can you tell me how the density depends on temperature?
Well, we have to find the function.
We do. Do you remember a function that has density, or let's say mass and volume and temperature in it? And it might even have a pressure in it?
Oh yeah, the ideal gas.
The ideal gas law, right? So we have what's called an equation of state. And I've used this term before, but an equation of state is just like it's the equation which describes the state of the material. And one of those equations of state, they typically have the type of material, the pressure, and the temperature. One of those is the ideal gas law, which is P is equal to nKT, where N is the number of molecules per volume, and T is the temperature, and P is the pressure. So that doesn't have density in it, but this is the number density. So we just need to put this in terms of the mass density. And I can do that by remembering that if I take the actual density and divide it by the molecular weight of the stuff, right? This is a mass over a volume divided by the number per stuff, like the number or the mass per molecule. That is the number density. So I can just put this in here and say the pressure is equal to rho over mu, which is the molecular weight. I should probably be careful about that. This is the molecular weight. So for hydrogen, that would be 1. Helium, it would be 2, right? Times kT. So this is how pressure depends on density. So in a way, we are going to put in this this height dependent by taking this into account. Of course, now we're going to be dependent on temperature, which is going to be a function of height, and we're going to assume that the temperature is constant for the atmosphere, which is not true. But at least at first order, we can do that. So I'm going to go ahead and put these things in. Remind me, what is this thing? G, little g, right? So we can write this as minus little g times solving for density over here. This is going to be mu naught mp over kt times p. That's just solving this guy for density and plugging it in here. And so now I have something that has pressure and pressure, and I've got distance over here up in the atmosphere. Is that an integral that we can do?
Yep.
Yeah, it is an integral we can do. Sure it is. Sure it is. So this is an integral that we just do our separation of variables and integrate both sides. So I take my dp over p is equal to minus g mu naught, or mu mp over kt times p, I took that over there, times delta r, dr. So this is the integral we have to do. I'll let you do the right side first because it's easier. What's the integral on the right side?
All of that times r.
All that, yeah, it's just all that times r, because there's just an integral. We've got an integral from 0 to r. We're going all the way from the surface to the top. This is an integral from p naught to p. And this one is just going to be on the right-hand side, minus g mu mp over kt times r, because I'm going from 0 to r.
Fun fact.
Yeah.
Talking about Boltzmann's constant.
Yeah.
Yesterday was his birthday.
Hey, happy birthday, Boltzmann. Boy, it's been a good number of birthdays. And what about the integral on the left? dp over p. It's the logarithm. And of course, because we're physicists, we will not do the absolute value because we know better. Because that's not physical. But anyway, it's the natural log of p over p naught. So I'm going to take e of both sides, and you probably get what you expected. P is equal to p naught e to the minus g mu mp kt r. And we have a name for this thing. It's called the scale height. Sorry, did I do that right? Yeah, it's actually the inverse of the scale height. We're going to write this like this. P naught e to the minus r over h, and we're going to redefine h as kt over g mu mp. This is called the scale height. And it has units of What are the units of that? Meters. Yeah, well, it has units of whatever you measure R in. So this has units of meters. And for the Earth, if you put all that stuff in, it's about 8 kilometers. So we can use kilometers if we like. This is about 8 kilometers. So what does that mean? Well, let's go back to what we talked about originally when we started this. The scale height is going to change where this drops off, like 1 over E. So if I increase G, right, what's going to happen to the scale height? Wait, is that working? If I increase gravity, that's, oh right, yeah, increase gravity, what happens to the scale height? Make G bigger, what happens to H? It gets smaller, right? So if I double G, the scale height drops by half. So here's 8 kilometers, this is about 1 over E, and if I double G, I drop the scale height. So just as you predicted, a bigger, more massive planet has a thicker atmosphere that's closer to the surface. If I were to double T, that would make this whole thing shift up, and that would be 1 over E up at 16 kilometers, which, like you predicted, the temperature higher, we get a fluffier atmosphere. So what this H is telling you is how rapidly the atmosphere falls off by 1 over E. And it depends on temperature and gravity, so the scale height for Mars, we can do some pretty cool calculations. We can say, well, the scale height for Earth is equal to KT over G mu naught, or mu MP. That's the scale height for Earth, and that's the Earth temperature and the Earth gravity. But the scale height for Mars is going to be KT Mars divided by G Mars mu MP. And if we take, nitrogen, carbon dioxide, they have about the same molecular weight, don't they? To within a factor of 2. Wait, nitrogen is 28, and CO2 is 14 and 32. That's much larger. Okay, so we better leave that in there. Okay, so we'll leave the molecular weights in here. So I'll take the ratio of these guys. I want to know how much bigger or smaller is the Mars scale height. So let's take the ratio of these. I'm going to say H Mars divided by H Earth is just going to be the ratio of these, which is, I don't have to worry about K because that's the same in both. So I just have T Mars on the top. And I don't have to worry about MP, so I just get G Earth on the bottom, and I get mu Earth on the bottom. That's all divided by T Earth. Whoops, those should be Mars, shouldn't they? Because I've got Mars on the top. And then dividing that by the scale height of the Earth, I get T Earth over G Earth and mu Earth. So I can do a little calculation to figure out how much bigger is Mars scale height than the Earth.
What was
Mu is the molecular weight. So let's write down, well, let me write this down a little bit clearer here, and we can figure out what the ratios are. H Mars over H Earth is equal to T Mars over T Earth, right? Because we've got this over this. And then it's equal to G Earth, or times G Earth over G Mars, because I've got G Earth over G Mars in the numerators, or in the denominators. And then I have the mu Earth over mu Mars. Mu Earth over mu Mars. So now what are these numbers? What's T Mars? You remember? Surface temperature.
200.
Pretty close, 220. So we'll put in 220. What's Earth? 288. Okay. And what about G Earth?
9.8.
Can we use 1?
1.
Since this is a ratio?
Oh, sure.
Yeah. Okay. So how many G's is it on Mars?
Well, it's a 10 to mass, so we do 10.
But it's smaller.
Oh, right.
Yeah. We can calculate this out, but let's look it up here. I'm pretty sure it is 6/10, but let's see. Gravity on Mars. No. Oh, right. That doesn't work. Gravity on Mars. All right, 3.7. So what's 3.7 divided by 9? Is about a third. Yeah, so it's a third. So let's call this a third. And that's not 6/10, but close enough. And what is the molecular weight of Earth? We decided it was about 28.
That's 3 over 1, right?
Right, 3 over 1. Thank you. Because this is, right. How's that?
There we go.
Okay. This, though, we decided molecular weight of nitrogen N2 was 28. And the molecular weight of, oh, right, not CO2, oxygen. Oxygen and nitrogen, oh, sorry, CO2 because Mars has a CO2 atmosphere. So C is 12. Oxygen is 16 plus 16, so 32 and 12 is 44. So that's like a half. Okay? Order of magnitude. So what do we get here? We get, what's 220 over 288? That's 1-ish, right? This is 3, and this is half. So we expect H Mars to be about 3/2 of H Earth. H Earth is 8, so Mars would be 12, and it turns out to be about 11.3. So not bad. We didn't do too bad for making a bunch of approximations. So so Mars, the H on Mars is to first order 12. H on Earth is to first order 8. Now we're not going to do the calculation, but what do you think H of Venus would be? Now I'll give you a hint. This is approximately 1/2 still for Venus, right? This is about 1. So it's going to be about half the temperature change. So what's the temperature change on Venus? We've got 740 and 288, right? So what's 740 divided by 288? 2? 2.5. So 2 times 1/2. Scale height on Venus is about the same as Earth. Because even though it has higher temperature, the gas is twice as heavy. So it turns out to be about the same. So why does this even matter? Like, it doesn't matter. Why does this even matter? This matters because we can look at the temperature drop with altitude and look at how the scale height fits in for various areas in the troposphere. Because remember, the pressure is dropping off like this. The temperature is subjected to just thermodynamics, right? So we expect the temperature to drop with altitude, but that's not what's happening on the Earth. What's happening on the Earth? The temperature drops as a function of altitude until it hits the tropopause, and then what happens? It starts to go up. It stays constant for a little bit, and then starts to go up again, and then it goes down again, and then it goes up again. So what's going on there? It does have to do with the composition of different materials in the atmosphere. That's right. So the tropopause is where the temperature stops getting colder. And the reason we call it the tropopause is where all the weather is, right? And why does the weather stay in the tropopause? Have you ever asked yourself that? Why? It's not the pressure differentials. You can have clouds at any altitude if the temperature is right. In fact, we have stratospheric clouds on Earth, right? So what's going on, though? Now think about what happens as I take a gas. Let's take water vapor, which is the Earth's main gas. Water vapor is decreasing. Sorry, water vapor is there. Temperature is decreasing. What happens at a certain temperature with water vapor? It condenses, right? And so at a certain temperature, you condense water into water droplets, which we call clouds. Right? So as you're going up in the tropopause, you're condensing clouds, condensing clouds, condensing clouds, and it depends on pressure and temperature. But then if you're condensing clouds here and suddenly you get warmer, you're no longer going to condense any clouds. And in fact, this acts as a trap. All of your water condenses out before you get up here. The stratosphere and mesosphere are extremely dry. So this is called a cold trap. Right? It's keeping the water out of the upper atmosphere. But the reason this heats up is because you have oxygen up there still, which gets photodissociated into ozone. And ozone is a fantastic sink of UV radiation, and so it heats up. So this temperature change right here is due to the fact that you're heating up the atmosphere because of ozone. Where do you think the ozone level drops off? Where the temperature switches back again. And now you're just cooling off because you're getting further and further away from a warm thing, and it gets colder as you get further and further from a warm thing. And then you get to the point where, oh, hey, we're suddenly getting higher and higher temperatures again. Well, this is basically the edge of the, yeah. And so now we're depositing energy into the upper atmosphere from solar wind. Of course, the temperature up here stops meaning anything because it's so low density that what does it mean to be high temperature if there's only 3 particles per square cubic kilometer or cubic meter, right? It doesn't mean much. But the temperature change is telling you something about the pressure, but even more importantly, it's telling you something about the composition. So if we could measure temperatures in planets, in their atmospheres, you can learn about the composition of the planets. And you can learn about the volatiles of the planets and what those volatiles do. Because this right here tells you exactly, if you were an alien from another planet and could somehow measure this, you would know at exactly what level we had weather and where our clouds were and what type of volatiles we could have rain as. On Mars, for example, you have CO2 clouds, not just water clouds. Water is the only thing that really condenses in our atmosphere. On Venus, you have sulfur dioxide clouds and hydrosulfuric acid clouds.
And rain.
And rain in some levels of the atmosphere. And water clouds. It's just you have to go way up to the very tippy top of the atmosphere before you see the water clouds. In Jupiter, you have water clouds, methane clouds, ammonia sulfate clouds, right? Because they've got all the things in there. So this temperature and pressure stuff is telling you about the structure of the atmosphere. All right, so I think we already talked about, you might try and ask yourself, why does the tropopause vary with position on the planet? And that's going to be a function of both temperature and pressure, and also on ozone composition, right? It also has something to do with the fact that we're a spinning object. And if you can see this picture up here, we're spinning, so the pole's atmosphere is thinner. Like for the same pressure, it's closer to the ground because we're spinning around, and that's going to drop our tropopause. All right, so that's the Earth's atmosphere. We're going to come back and talk about other atmospheres later, but I want to see if there are any questions about the Earth's and its atmosphere before we move on to our companion object, which has no atmosphere. Any questions? So what is our companion object? The moon. Does the moon have an atmosphere?
No.
Why not?
No gravity.
Doesn't have as much gravity, right?
No gravity at all.
No gravity at all, right? I shouldn't show you this picture first, but I'm going to because it's awesome.
That's space 3.
What? Yes, I'm sure it is. I don't know. I don't even know what you're talking about. So the first question, what's that? This is an idea of what happened, and I'm just going to list these out because how our moon formed is kind of an open question. The main idea, the main consensus is that it was a giant impact. Other ideas could be fission, that we basically had a spinning Earth and the moon just went, right? The problem with that is that it doesn't have, the moon is not in the equatorial plane. It's in the plane of the solar system. It's not, so that doesn't make any sense. If it came out from spinning, it would be in the equatorial plane. And also there are observed chemical differences. If moon and Earth formed out of the same stuff, you would expect similar chemical compositions. One possibility is capture. So here's the Earth, and you come by, and the moon just goes, whoop. How likely does that look from your physics perspective? If you were playing a video game and suddenly, you drove a car and did something where you had something going really fast, and then you tugged on it with a little force, and it went whoop. You'd say, that's totally unphysical. I'm not playing this game anymore, right? So the problem is its energy considerations. You don't do that?
I don't think I've played that game, because that sounds like a really lame game.
It is the game where you're driving a car and then a little force pulls on you and you go whoop. You win. Yeah. So there's energy concerns, and all of the ways that we could fix this by like having a third body come in or some are just difficult to explain. Co-creation, again, there are different compositions. That would be they just form near each other, but they're different compositions. So the idea is that it formed through something like this, which some people call this impact-assisted capture. Because it really is a capture. We just, So what happens in this thing, I think I've got, do I have a picture of it? No. What happens is this thing comes in and rips off half of the core, or half of the crust and mantle of the Earth. And the core of this thing falls into the center of the Earth during differentiation, and the rest of the object that forms out of the debris of this impact is devoid of what you would expect to see from the core material. And so that explains the chemical composition differences, because it really did form from a different subset of materials. It also explains why there's very few volatiles, because they got blasted off during the impact, rained back down on the big planet, and the little planet didn't have enough stuff left over. But there are some problems with this. The first people to do the modeling of this only modeled the impact part to get the ratio of masses, like how big of a planet would you have to be hit by, how much would you get out. It has only been recently we've been able to do models that do the subsequent formation, and it turns out this is really hard to get a moon in a nice circular orbit, if you think about it. Right, because this is going to blast material off like, which is going to go on an elliptical orbit, and then somehow that, how does that work? How does that get back into a circular orbit? So that's a problem. But it's the best idea we have at the moment to how we got our moon. But the most important thing in my mind about the moon is that it doesn't look anything like the Earth, and therefore we have a little laboratory, because we have Earth, non-Earth, at the same distance from the sun. It's like you couldn't even design it. The only better experiment would be if you could, because if you made it the same size as the Earth, you'd have two Earths. And that's not a good experiment. That's like having two control Earths. So it's like we have a control object which nothing happened to it. And then we had the experiment called the Earth. And there was no change in the control Earth. Does that make sense? It'd be even better if we had like 6 moons of all different sizes. But we didn't set it up that way. But the most important thing about the moon, and this is going to be relevant to our activity for next time, is the fact that you can see its entire history literally written on its face in the cratering history of the moon. And the fun thing about craters is that because you're basically looking at a geological process, if you see more craters, you know that surface has been exposed longer than the ones with fewer craters. So you can use craters, if you can find some way to calibrate it, you can use craters to date the surface of an object. Because if you've got 100 craters per square kilometer, that surface is 3 billion years old. And if it's 50 craters per square kilometer, it's 2 billion years old. But we have to find a way to calibrate that. We have found a way to calibrate that. We've gone to the moon and brought back rock samples and dated the rocks. And so we can look at, there are 5 points on the moon, and I don't have them up here, but they're like, Apollo 11, Apollo 12, Apollo 13, all the, or not Apollo 13, Apollo 14. We have all these places where we have samples from the moon. We have ages for those samples, and so we can count the number of craters on those things, and we have a date for the rock sample. And this is important because if you look at the backside of the moon, and I should probably point out that we don't have any samples of the backside of the moon, so we have to extrapolate from our stuff from the front side of the moon. There are main differences between this, right? More craters,
So the
right?
backside of the moon is more 3D than
That's, well, the front side's always facing us. So then when there was volcanism, those volcanoes came out and lava flowed over the front. That's what all those mares are. And that covered up the craters, right? But there are places on the front side that have similar crater densities. They're mostly down here. We have no ages for those. But there was one mission, where we went someplace in the Lunar Highlands that had craters. So while we have calibrated this, if anybody ever tells you we've gone to the moon and done the moon, we have not. Because we went to, what, 11, 12, 14, 15, 16, 17, 18? Or did we not fly 18? 17 was the last one. 6 locations on the moon. We have 6 ages and 6 crater densities, which we have now used to extrapolate to the age dating of every object in the solar system.
That's good enough for an intro physics lab.
Yes, and that's what we're going to do next Tuesday, is we're going to do that lab, right? But the problem is that, I mean, do you trust that? Like if you use this to measure the ages on Mars or Venus or whatever, do you trust that? I don't trust it.
Well, I mean, compared to the fact that we've basically been extrapolating what we know about Earth to the entire universe.
Yes, exactly right. Now, yeah, it's certainly better than 1, which is what we've been doing on the Earth. Yeah, that's a good point. So that's the great thing about the moon. But really, the moon, you know, if you think about our lunar exploration, we sent a bunch of non-trained scientists. Sorry, we sent 1 trained scientist, a bunch of extraordinarily well-trained pilots to the moon. They walked around on the moon. They took rocks from the moon. They sat on the toilet with the moon. No, they took rocks from the moon, and then they brought them home. 400 kilograms from 6 locations. That's not very much,
Well, it would be
right?
like,
1 geologist did that. What's that?
I say it'd be like a geologist from another planet coming to Earth and just doing things up in like Canada,
Yeah.
Russia, and say, oh, it's a frozen planet.
Yes, exactly right. Now, we did try to get as much variation as we could, but if you think about it, we're trying to be safe and get these people back alive, so where did we mostly land? The flat spots,
So,
right? Yeah.
question, why do we not put a rover on the moon?
Well, that's a great question. That's a great question. I would love to put a rover on the moon. The problem is that to do the age dating, you have to bring the rocks back.
We can do that eventually.
I think so. And the cool thing about the moon is that on Mars, to drive a rover, you have to send instructions and have to wait an hour and a half to hear back. On the moon, you could like drive it practically in real time. There's like a second delay. So no, this is one of the things about NASA that kind of gets under my skin, is that they want to skip over the moon and go to Mars with people. But that doesn't make any sense at all, because the moon is really close. If something happens to them on the way to the moon, they come right home. And we have a lot of practice to do, and there's tons of science you can do on the moon. I think a lunar base makes a heck of a lot of sense. In fact, the thing that makes the most sense is a lunar base with telepresence around the whole thing. And you drive robots on the far side, and you live on the front side.
Besides, how cool would it be to look at the moon and I can see a little glowing city on it?
I'm on your side. Vote, people. The moon deserves a vote. So, all right. So if I hand this out to you, do you promise to bring it back? Because I want you to read this before we do it.
Also, are we ready to get back to that spectroscopy?
Probably.
Okay.
Yeah. I kind of forgot to ask for them back.
Oh, well, I turned my
I know you did. A couple people did.
Okay.
But I'll get yours back to you.
Okay.
Yeah. So let's do this. Why don't you come up and pick up these guys, 1 each. Now this was an activity that I took from a planets course that I used to teach at the University of Washington. It's a little, no, I think it's a good level for us. I mean, log plotting with isochrones on it. I think we're good. We can handle it. But I may ask you some more in-depth mathematics questions at the end. So just read, don't do this though. We're going to do this in class.
Okay.
So just read it, hold off. And I say don't do it because there's actually a lot of work counting. And if you do that ahead of time, you won't have anything to do. So.